Continuing 9.4, Weather Processes. Jet streams are big shakers in atmospheric circulation. They are narrow, fast-moving streams of air caused by temperature differences between two air masses. They are near the top of the troposphere and move west to east in both hemispheres. There is a stronger, more organized polar jet and the weaker subtropical jet, as labeled in the cartoon. The jet streams are from about 160 to 310 miles wide and are several miles thick. They travel faster in the winter, about 110 miles per hour, and slower in the summer, at about 55 miles per hour. These cartoons show the jet stream in relation to the major circulation cells. You can see the image below that the polar jet is actually lower in altitude as compared to the subtropical jet. We've already been talking about pressure, and how that makes air move around. But here are some more ways to think about how air moves. Unstable or stable air refers to the atmospheric stability, which is the tendency of air to remain in place. If air is stable, air parcels resist movement or return to the original spot after they move. In unstable air, parcels are rising until they reach air of similar temperature and density. Air is unstable when lighter, warm, or moist air is overlain by denser, cold, or dry air. This is associated with severe weather. The picture is of a weather balloon, but is meant to give you a concrete idea of an air parcel. However, when thinking of weather systems, our air parcels are much huger. We will next be discussing about the boundaries between these different air parcels. Fronts are the boundary between cooler and warmer air masses. A cold front occurs when cold air is moving into warm air. A warm front occurs when warm air is moving into cold air. A stationary front occurs where the boundary shows little movement. And an included front occurs where rapidly moving cooler air overtakes another cold air mass, wedging warm air in between. Let's look at the cartoons. Quick, hopefully easy quiz. What types of fronts are depicted here? Hopefully you got it. Got it right. Cold front on the top cartoon, warm front on the bottom cartoon. What are some major differences between a cold front and a warm front? Did you notice the different geometries of the fronts? Does this make sense considering what we know about the relative densities of warm and cool air? Cold air wants to stay down, high pressure. Warm air doesn't mind rising. Cold air pushes the warm air up pretty quickly, which does what? As the warm air is forced up rather quickly, it cools and clouds form, and boom, we have a cumulonimbus cloud and a storm with lightning and thunder, maybe hail too. Awesome! Compared to the warm front. The warm air gently rises up the back of the cold air mass. As the rise is more gentle, the cooling and condensing is also more gentle. At this front, we generally get more gentle rain over a wider area. More cartoons! On the top we have our cold front and warm front. Nice and familiar from the previous slide. On the bottom we have an occluded front and a stationary front. The stationary front isn't going anywhere for a while. The cold and warm air masses have reached a truce for now. In an included front, a cold air mass is bulldozing into the back of another cold air mass, pinching the warm air mass between them. And we know what happens as a warm, moist air mass is forced into higher altitudes, right? It cools, forms clouds, and often causes precipitation. Next set of cartoons. At the top we have some front depictions you might remember seeing on weather maps. The cold front is more violent with sharp, cold, blue teeth. The warm front has more gentle, rounded, and red-looking teeth. Occluded is confused, but still has its teeth pointing the same direction. So it still has some bite. Stationary has its teeth missing or on both sides. Totally not biting. Below are the same cartoons described in the previous slide, just for reference. On to the Coriolis effect. This is the deflection of wind due to the rotation of the Earth. The wind is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. Get out your right and left hands and let's look at the cartoon on the world. We are wind, traveling from the equator to the North Pole. How are we deflected? To the right, which means east. We are now the wind traveling from the equator to the South Pole. How are we deflected? To the left, which means we are again traveling to the east. You can do the other directions yourself if you need the practice. This effect, the Coriolis effect, controls prevailing wind patterns. It is also important in hurricane formation. Interestingly, the faster the moving air or object, the greater the Coriolis effect. And it produces trade winds, which is spectacularly important if you are trading using a sailboat, or just sailing, or even cast adrift at sea. It also is super important in airline travel. Take a look at the cartoon of the world. You can see the major circulation cells with warm, moist air at the surface that rises to become cool, dry air. Which falls to become warm, moist air again. But I want you to also notice the deflection of the wind at the Earth's surface. To the right in the northern hemisphere, to the left in the southern hemisphere, creating trade winds. Let's start at the North Pole. We have the polar easterlies. Wind is named from where it comes from. It is heading west from the east. Then we have the westerlies from the east coast of the United States to northern Europe, creating some zippy trading lanes. Then the sad horse latitudes, where no wind was taking you anywhere, so historically you threw the heavy, useless stuff overboard, such as horses, so that you could row yourself back into some wind. Further south, you have the northeast trade winds. Remember, winds are named for where they come from, not where they are going. At the equator, you have the doldrums, no dominant winds. Below the equator, you have the southeast trade winds. We're deflected to the left now. Then the westerlies, and then the polar easterlies. Lots of words, but it makes sense, right? We already know why the general circulation cells occur with their general weather pattern. Now we know why we have these dominant trade winds. We've got it all figured out. Well, at least generally, anyway. 9.5. Hazardous weather and geographic regions at risk. There are many types of hazardous weather. We will be discussing the big ones. Thunderstorms predominantly occur in equatorial regions and are most common in the afternoon or evening hours in spring or summer. Of course, thunderstorms occur elsewhere as well, but the largest number of them occur towards equatorial regions. 3 conditions are necessary. 1. Warm and humid air in the lower atmosphere, creating very unstable air. 2. A steep vertical temperature gradient, such that the rising air is warmer than the air above it, i.e. cold air over warm air. 3. An updraft must force air up to the colder upper atmosphere fairly quickly. These totally make sense knowing what we know, right? If not, think about it. Perhaps watch the lectures again. Read your book more. It makes sense. This map is of the contiguous United States. It depicts number of days with thunderstorms annually. Where are the most thunderstorms? Right, interior of Florida, with over 100 thunderstorms a year. Definitely has warm, moist air. How about how many thunderstorms do we in the Nampa-Boise area get each year? I'd say less than 20. Agree? What's the general pattern? I would say a gradual increase in the annual number of thunderstorm days towards areas that are warmer and moister in the deep east, deep southeast. Agree? There are several stages in thunderstorm development and dissipation, and we will go over them in a little bit.